Okay, welcome back. So just keep going for our exercise. For the second exercise, the topic we have discussed with the fluid jet. So as showing the cartoon figures, in here the concrete flows into a car sitting on a scale, a radius scale. And here is a concrete flow. And the concrete floor has a density 150 pound mass per ft cubic, and the area of the concrete floor is 1 ft squared with a speed of the v 10 ft per second. And as at the instantaneous time stage, the weight of the car plus the concrete is the 800 pound force. So please determine the tensions in table. So because the concrete flow shoots into the car will let the car move to the right, but also we need the additional tension force to hold the car didn't move. And what is the weight recorded by the scale? So we have the weight is the normal force N recorded by the scale. So we based on the momentum equations, we know that the external force is equal to the total momentum change in the control volumes with the time plus the net momentum flow. But we actually know that the momentum accumulation term in this problem is non-zero because the concrete flow always input to the car. However, at the instantaneous time stage, the volume, the momentum changes in the control volume is quite smaller. So we ignore the effect for the momentum accumulations. So the external force is directly to be equal with the net momentum. So if we consider our problems along the x directions, so we know that the force along the x only have the tension force and is equal to the momentum contribute from the inflow. There is no outflow momentums. And we know the inflow, we have the minus m rate, and we convert the flow velocity to the x directions is the v cosine 50 degree. So we know the tension force is equal to m rate v cosine 50 degree. So the major questions for this equation is what is the m rate? So we know that the m rate, if we know the rho and we have the A cross-section area multiply the velocity, and then we can compute the mass flow rate. So what we have? We have the density 150, and we have the cross-section area 1 ft squared, and we know that the velocity flow is 10 ft per second. So it is equal to the 1500 the bomb mass per second. So we put the mass flow rate back to the equation in here. So we can rewrite the tension is equal to the 1500 bomb mass per second multiply the 10 ft per second and multiply the cosine 60 degrees. And we use the calculator to compute the answer in here. The 1500 multiply 10 multiply cosine 60 degrees is equal to the 7500, and the unit in here is the bomb mass ft per second square. So we know that the one bomb force is equal to 32.17 bomb mass ft per second square. So we need to divide the 7500 by 32 1.17 to convert the unit to the bomb force. So finally we know that the answer for the tension force is equal to a 233, around the 233 bomb force. So we answer the first question for the tension force. How about the second question? We need to know that the weight. So we change the force balance along the y. Here we use the z, so around the z directions. So we know that the force for the z directions, we have the weight downward, and the normal force is upward, so it's the positive. So here is a plus normal force is equal to, we don't have the outflow moment, so we only have the inflow moment. But so because the inflow, so it's a minus mass rate, but we project the flow velocity to the y direction is downward. So this is a minus v sine 60 degree. Okay, so we just reorganize the equation. We know that the Newton normal force, this is a normal force, is equal to W plus the m rate v sine 60 degree. Okay, and we know the W is the total weight of the car plus the concrete is 800 pound force, and need to plus the mass rate is the 1500 multiply the 10 ft per second velocities and multiply the sine 60 degree, and we need to divide it the 32.17 to convert the unit to the bomb force. Okay, so this is also the 800 bomb force multiplied the 1500 multiplied 10 multiplied sine 50 degree, and divided 32.17 is equal to around 403.8. So finally we know our normal force is equal to the 800 plus the 403.8, so it's a 1203.8 bomb force. It is our normal force for our systems. Okay, so for these questions we have the full jet. So if there is no tension force, the car will move into the right hand side, but we require additional tension force to hold the car didn't move. Okay, and you see the normal force is quite larger than the total weight of the car plus the concrete, 800 years. That's because the concrete flow hit the car to enhance the vertical force. Okay, so the slide just summarizes the key knowledge for this exercise. The weight recorded by the scale is larger than the weight of the car because of the momentum carried by a fluid jet. Okay, so the next exercise, the target related to the fence. As you see, the one fluid jet striking a flat fan, showing here. So there are some tips for this kind of the problems. The tip one, we assume that the V1 equal to V2 and the V3 if the flow condition is in fixed flow and the neglect elevation changes. So it's just based on the Bernoulli's equations because we know that there are in the same straight lines for our problems, and so following the Bernoulli equation, we know that the P1 plus the gamma Z1 plus the 2 over rho V1 squared is equal to the P2 multiply the gamma Z2 and the 2 over rho V2 squared and also equal to the P3 plus gamma V3 and plus 2 over rho V3 squared. Because the system is posed on at the atmosphere environment, so the gauge pressures at different cross-sections are zeros. And since here we say that we neglect the elevation changes, so there's no any elevation difference between three cross-section boundaries. So if we also assume the flow is incompressible flow, so actually we know that the V1 is equal to the V2 and equal to the V3. Okay, and the second tips, each momentum flow are equals. That means the inflow always equal to the outflow momentums. So the inflow, what is the inflow? The inflow in here is the net flow rate 1 multiplied the V1 is our inflow momentums. The outflow momentum is the net flow 2 V2 plus the net flow 3 V3. And the relationship between here for the inflow and the outflow need to balance. And for this problem, because this is a flat fence, so we only have the normal force perpendicular to the flat fence. So this is only the force in our systems because there's no any pressure gauge for the control surface boundaries because the system is closed on the airs. Okay, so the final tips, the jet does not cause a net force at the control surface because the pressure in the jet is atmosphere. Okay, so what's the problem? We can apply the momentum equation to the fan problems. So as you see, there is a water jet. Okay, and the water jet, we have the law for the water is the 1.94 slug per ft cubed. And we know 1 slug is equal to 32.17 pound mass. So it's also equal to 62.4 pound mass per ft cubed. Okay, and its defective 60 degrees by a stationary fan as shown in the figure. Okay, and then the incoming jet has a speed 100 ft per second with the diameters of 1 inch, and 1 inch is equal to 12/1 ft. So please find the force exerted by the jet on the fan. So if we go back to the cartoon figure shown here, it's by the jet on the fan. So the jet first will push the fan to the right. So it's the jet acting on the fan, just push the fan on the right, and because the fan will also push the water jet downward. So reaction force for this is the upward, because the fan will push the water downward. So the force along the y directions by the jet on the fan is upward. Okay, so for our systems, we assume we have the reaction force Fy downward and Fx have the left directions. Okay, as the cartoon figure shown here. The left hand side there is the force diagram, the right hand side is the momentum diagrams. And we assume the jet velocity is always constant, and the diameter also a constant, because this is based on the continuity equations. And for our questions, we neglect the gravity effect. Okay, so go back to see. We make the force balance and the momentum balance along the x directions. So first we have only the one force along the x direction is the minus Fx. Okay, and the Fx is equal to the momentum balance along the x directions. So there is the outflow momentum. So the outflow momentum mass rate V project to the x directions. Okay, project to the x directions. So the V multiply the cosine 60 degrees, and we have the inflow here. So minus the M rate V is the inflow. Okay, so we organize the equation Fx is equal to the mass rate V1 minus cosine 60 degrees. So what is the mass flow rate? So the mass flow rate, if we know the density and we know the cross-section areas and we have the velocity, and we can compute the mass flows. So in this problem, we know that based on the continuities, so the mass flow in is equal to the mass flow out. And then if we still have the V inner flow and the V outer flow are equals. Okay, so we just compute the mass flow. We have the density in here, the 62.4, and the areas. We have the diameter of the flow is 12/1 ft. So this is 4/pi, and the 12/1 square is 4 pi d squared. and multiply the flow velocity is the 100. Okay, so it is equal to, you can compute by your calculator, the 62.4 multiply the pi and multiply the 100 flow velocities divided the 4 and divided the 12 square. So the mass flow rate is 34.01 pound mass per second. Okay, so we go back to the force balance. So we know that Fx is equal to 34.01 and then multiply the velocity. The velocity is 100, and there is 1 minus cosine 60 degree, and we need to convert the force to the bump force. So here we divided the 32.17. Okay, so use our calculators, the 34.01 multiply 100 and multiply 1 minus cosine 60 degree and divided the 32.17 to convert the unit to the bump force. So finally, the bump force is equal to 52.87 bump force. This is the Fx force, and what's the question? The question is the boundary force exerted by the jet on the fan. So this is right. This is the force directions contributed by the jet on the fan. So this is one of our answers for X directions. Another is we are focused on the Y directions. So for Y directions, we have the minus Fy, and we neglect the gravity effect, so we don't have the weight contribute from the fluid. And is a balance for the momentums. Here we only have the momentum along the Y directions contributed from the outflow rate. So there is the outflow momentums, and we project the velocity of the flow is downward. So this is outflow, so it's the mass flow rate multiplied the flow velocity project to a Y direction, so it's the sine 60 degree, but the flow direction is downward, so there is the minus. So we know that the Fy is equal to m rate v sine 60 degrees. So the m rate here again for 34.01 multiplied by 100 ft per second multiplied by sine 60 degree divided the 32.17 to convert the force unit to the bump force. So 34.01 multiplied by 100 multiply sine 50 degrees divided 32.17. So the answer is equal to the 91.6 bump force. If you take a look for our questions, it's required to answer the force by the jet on the fan. So because the fan will push the water downward, so we need additional force upward. This is our Fy directions to acting on the fan. So this is our additional solutions for the force acting on the fans from the jet. Okay, so until this exercise, we also know that the pressure force are still zero because our environment is exposed on the atmosphere environment. So the gauge pressure is always equal to zero. So right now we have this second type conditions is the nozzle. The first one is the nozzle. In the nozzle, the difference is the cross-section area A are inside the pipe, so they will have additional pressure force, the PA multiplied the cross-section area A, provided additional pressure force, but on the right-hand side cross-section area B is exposed on the atmosphere environment, so the gauge pressure still equal to zero. So for the nozzle problems, we have one side inner pressure force, another side is still have gauge pressure equal to zero. So usually for this problem, we will find out the pressure at the cross-section area A by the Bernoulli equation between the A to B. And if the velocity flow is unknown at the station A and B, usually we will apply the continuity to calculate the flow velocity BA and BB. So for this chapter, you still need to keep in mind for the Bernoulli equation and the continuity equations. So let's move to the next exercise. This is example for the nozzle. Okay, so the figure shows there is airflow inside the nozzle pipe, and we know the inlet pressure P1 is equal to the 105 kilopascal. But you take a look, this is absolute. And we know that the atmosphere pressure is 101.3 kilopascal absolute. So the gauge pressures along the cross-section 1, we need to minus the environment pressure 101.3 kilopascal. So the gauge pressure at the cross-section 1 is equal to 3.7 kilopascal. And the nozzle has an inlet diameter E1 is equal to 0.06. So that means the cross-section area of the A1 is equal to 4 over pi D1 squared. If we calculate the answers by the calculator, for the pi multiply the diameter squared 0.06 multiply the 0.06 and divided the 4. So the area of the cross-section F1 is 2.826 10 minus 3 powers. And we know that the diameters on the cross-section area 2 is the 10 millimeters. For D2 is the 0.01 meters. So we know that the A2 is the 4 pi D2 squared. So that means it is the pi divided the 4 multiply 0.01 and multiply 0.01 again. So the air cross-section area of the 2 points is 7.8510 minus 5 powers meter squared and meter squared. And the pressures are on the cross-section area 2 is equal to 0 because it's exposed on the air atmosphere environment, so the gauge pressure always equal to 0. So in that case, the nozzle is connected to the supply pipe by the flange. So if the flange to hold on the pipe didn't move, so please find the force required to hold the nozzle stationary. Okay, and assume the air has a constant density is 1.22 kilograms per meter cubic, and neglect the weight of the nozzle. So this problem is quite simple. We only need to focus on the directions along the axis. And based on the force diagram shown here, we know that the required force to hold the pipe is F shown here. So along the x directions, the force balance is the required force plus the P1 multiplied A1, because this is additional force contributed from the inner pressures, okay, and need to equal to the momentum outflow minus the momentum inflow. Okay, and we need to answer questions how large it is of the F is equal to the M rate B2 minus B1 and minus P1 A1. So for these equations, there are two unknown parameters is V2 and V1. So the first, we have the continuity equations. So we know that for this problem, we know that the V1 A1 should be equal to the V2 A2, and we assume the V1 is equal to the V2 multiplied A2 divided A1, and we have the A1 here and we have the A2 here, but we know that the diameter also, so the V2 is equal to the D2 divided the D1 squared. So we know that the V1 is equal to the V2 multiply the diameter ratio squared. So D2 is 0.01 and the D1 is 0.06. And then we compute the ratio and have the square operators. So here is equal to 0.0278. This is a continuity equation provide us the ideas the relationship between the V1 and the V2. And the second, we have also based on the Bernoulli equations, and we know that the P1 pressures plus the gamma V1 plus the 2 over rho V1 squared is equal to the P2 multiplied plus the gamma G2 and plus the 2 over rho V2 squared. Because they are located at the same elevation, so the V1, V2 cancel out, and we don't have the gauge pressure at the cross-section area 2. So we can reorganize the equations. Is a P1 gauge pressure equal to the 2 over rho and V2 squared minus the V1 squared. And we know that the V1 is equal to the V2 multiplied by the 0.0278. So here we can rewrite the equation and keep the V2 squared, but the V1 replaced by this relationship. So this is V2 squared multiplied 0.0278 squared. And we take the V2 squared outside, so this 2 over rho V2 squared, and inside we only have the 1 minus 0.0278 squared. Okay, so that means the V2 squared is equal to 2 times P1 divided the rho and divided the 1 minus 0.0278 squared over 1. Okay, so it is equal to 2 times pressure 1 is 105 kilopar, and divided the rho, so is the air 1.22, and divided the 0.0278 squared, 1 minus it. So here is the 0.9992 over 1. Okay, so the 2 multiply the 105, and multiply the 1000, divided the air 1.22, divided 0.9992. So it's equal to 172.268.9. So the V2 is root of this number is equal to the sorry, so there are some troubles. We take a look. Here is 0 point square, so the P1 is equal to 2 over rho, and this is 2 times P1 divided rho, and divided the 0.9992. So I recalculate the number. Wait. So I check the numbers. So again, sorry, the 2 times pressure. The pressure is not the 105 because we need to put the gauge pressure. So here is 3.7. Okay, so we recalculate the values. So the 2 multiply 3.7 multiply 1000 divided the density 1.22 divided the 0.9992. So here is the 6072.4, and then we calculate the root of this number. So the V2 velocity is equal to 7.9 in meter per second. And then we put the V2 back to the equation. We can calculate the V1. So 77.9 multiply 0.0278. So the V1 velocity is 2.16 meter per second. Okay, so right now we have the V1, V2, and you see the equation showing here. So we just put the V1 and V2 go back to the equation in here. So the force is equal to the mass rate multiply the V2 is 77.9 minus the V1 is the 2.16 and minus the pressure gauge P1 is 3.7 multiplied 1000 kilopascal and multiply the A1 area. The A1 in here is 2.826 multiplied by 10 minus 3 powers. So the only one unknown parameters in here is the mass rate. So we know that the mass rate is equal to the rho AV. So we just take maybe the A1 and the V1 to calculate the mass flow rate. So density is 1.22 and the A1 here is the 2.826 and minus 3 powers, and the V1 in here is the 2.16. So we can calculate the mass flow with the 1.22 multiplied by 2.826 and then multiply the 2.16 and divided 1000. So here the mass flow rate is 7.447 10 minus 3 powers. So it's a kilogram per second. So put this number back to here, so we can calculate the mass flow rate multiplied 77.9 minus 2.16. This is equal to 0.564 newtons minus here is the 3.7 multiplied 1000 multiplied 2.826 divided 1000. is equal to the 10.45 newtons. So finally, is equal to the minus 9.89 newtons. So this is F equal to the minus 9.89. That means there is a negative, so the force direction is on the left hand side. Okay, but you go back to see that initially we assume the force is the positive on the right hand side. So no matter initially you assume the force directions, if finally you compute the answer with the negative, that means the directions need to convert to the opposite directions. Okay, so the next slide just summarize. If the answer for the force is negative, then the force acts in the direction opposite the chosen directions. The chosen direction is initially we assume the direction is on the right, but finally because the answer is negative, so the force is opposite. Okay, so let's move to the another exercise. We call that is pipe beds. How different it is. For this exercise, we have both sides have the pressure because the cross section A and the cross section B are inside in the pipe, so the gauge pressure are not equal to 0 both sides. In that way, we need to consider two pressure forces inside at the different cross section area A and B. So what's the problem it means? We have the 1 meter diameter pipe band showing the diagram is carrying the crude oil. So we have Sg is equal to 0.94 with a steady flow rate Q. So we have a discharge is equal to 2 meters cubic per second, and the band have a 30 angle and lies in the horizontal plane. So the pipe is just put on the horizontal plane, and the volume of the oil in the band is equal to 1.2 meter cubic, and the amplitude of the weight for the band is the 4 kilonewtons. This is for the empty band pipe. So assume the pressure along the center line of the band is constant. So the pressure is constant values is 75 kilopascal. So find the force required to hold the band in place. So the force will contribute from the flange, and the flange can hold the pipe didn't move. So for this problem, because we see that the force diagrams we assume the supported force along the y is Fy, and along the x is Fx. And because the pipe put on the horizontal plane, so we have the vertical force overcome the weight. Okay, so we first take a look along the x directions. So for the x direction, what kind of force we have? First, we have the Fx, and we have the pressure force on the left-hand side is the positive. We have a pressure force on the left-hand side, and we have the pressure force on the right-hand side. Also, the pressure multiply the cross-section area A, but we need to project to the x directions. So need to have the cosine 30 degree, but the direction is the negative directions. So we have the minus here, and it's equal to a momentum balance. So what is the momentum balance along the x directions? Here is the outflow. So we have the outflow mass rate V multiply the cosine 30 degrees, convert the mass flow rate multiply the V, convert to the x directions. And there is the inflow along the x direction, so we minus inflow rate. Okay, we just reorganize the equations. So Fx is equal to the m rate v, and there is cosine 30 degrees minus 1. Also, we move the pressure force to the right hand side. So there is the plus the PA, and also the cosine 30 degrees minus 1. So we just also reorganize the equation. So the mass rate V plus the PA multiply the cosine 30 degree minus 1. So what is the mass rate? The mass rate, since we have a Q already, so the rho multiply the Q will equal to the mass flow. So what is the rho? The rho, we have a specific gravity Sg is 0.94, and multiply the water density, and the Q is the 2. So this is the mass flow rate is equal to 0.94 multiply 1000 multiply 2. So this is equal to 1880 kilograms per second. Okay, and what is the area? What is the area? Because we take a look, we have the Q, and we know that the Q is equal to the area multiplied the velocity. So the area is can compute from the Q divided the velocity flow. Okay, so what's the flow rate for these questions? Okay, so we take a look. We need to have the okay. So the answer the question tells us the diameter is 1 meters. So we don't need to compute based on the discharge. We can directly to compute the area. It's 4 over pi 1 square. Okay. So we can compute the velocity by the Q divided the A. Actually, our Q is 2 meter cubic per second, and divided the pi divided 4. So what is the flow velocity? The flow velocity is 2 divided the pi and then multiply the 4 is equal to 2.55 meter per second. Okay, so we have all of the number we need to compute the Fx. So we just put a number inside the equation. The mass flow is the 1880, and multiply the flow velocity is 2.55, plus the pressures here is 775 kilopascal, multiply the area is the 4/pi 1 meters square, and the cosine theta, cosine 30 degrees minus 1 is equal to the minus 0.13. Okay, and here I just compute the number by calculator. 1880 multiplied 2.55 plus the 75 multiply the 1000 multiply the pi divided the 4. So here is the 63669 multiply the minus 0.13. So it's equal to the minus 8276.9. Okay, and the unit is the newtons. So as you see, the FAKs is the support force contributed from the flange. So the FAKs is the minus. So that means the force directions is along the left side. Okay, so this is the answer for X directions. So how about the Y directions? So if we go back to see the force diagrams, we only have the force along the Y direction. First is the Fy, and another force is contributed from the pressure force, and the pressure force is upward. So it's plus the PA sine 30 degrees is equal to the only have the one momentum flows along the Y directions, and this is the outflow momentums. So the mass rate multiply the V sine 30 degrees, but the direction is downward, so there is the minus. So we make the balance, so Fy is equal to the minus m rate V sine 30 degrees minus the PA 30 degrees. So the Fy is equal to the minus m rate V plus PA multiply the sine 30 degree, and then it's equal to the minus, which I put the number is the 1880, and the velocity is the 2.55 plus the pressure is the 75 multiply 1000, and the area is the 4/pi 1 square, and multiply the sine 30. So we can compute the answer is also the minus, and because the time limit, so you can calculate by yourself. It's around to the 31.8 kilonewtons, but the direction is downward. Okay, so the finally is the z directions. It's the support force to overcome the weight. Okay, so we have the weight force. So what is the weight? The first weight we have the empty weight of the band is the 4 multiplied 1000 Newton. But this is only for the empty band. Need to plus the oil's weight. So what is the oil weight? We have the gravity, specific gravity 0.94 multiplied the gamma W is 9810, and the volume in here is 1.2 of the oil volumes. So the final answers is equal to the 15.1 kilonewtons, and this force is the positive to support the total weight. Okay, so this is the final exercise today, and the difference compared with the pipe band to the nozzles. The pipe band both sides have the pressure force, but the nozzle only have one side have the pressure force. It is very important for the crushings of the nozzle and the pipe band. Okay, so right now I would like to highlight the quiz on the next Mondays. OK， 所以我们下个礼拜一的考试重点，第一个一定会用到这个动量方程。那用到动量方程，通常就会去问你一个问题，就是到底我们需要多少的力量去阻挡这些 fluid 作用在某些块体上所产生的这个 force。OK， 所以第一个一定会考。那我们大部分的问题可以回到我们这个地方，就是说我们有时候考虑的是喷射流，那这个喷射流可能会打在扇叶上面。那这样的问题，我们如果要让上叶不动，或者是让这个喷射流喷射的块体不动，那我们要多少力量才可以让这些东西不动？那这几个问题，比如说火箭或是这些喷射流，然后打在这个 fan 上面，其实这几个问题都是没有内压的，也就是说它们的环境都是在大气压力之下。可是在这个速缩流或是这种弯管，它们并不是完全暴露在大气里面，所以它们会有内压。那只是速缩管它的另外一侧是暴露在大气里面，所以它只有一边会有这个内压。那可是这个弯管因为两个断面机都在管内，所以它会有两个内压。所以这个几个问题都会有不同的这个外力必须要去考虑，所以我们一定会考一题，就是如何运用这个动量方程去做一个 force 力学上的平衡跟动量上的这个静动量流率的平衡。那永远不要忘记，其实就像最后一题，我们今天的例题这个弯管，如果你是在弯管里面，你就必须考虑的是这个内压的这个 pressure。那记得一定要再考虑这个内压的 pressure。那通常我们在考虑这些问题的时候，不一定会提供压力给你，也不一定会提供速度给你，所以有些时候你必须满足伯努利定律还有连续方程，额外去计算压力，或是额外去计算速度。 记得我们一定要有些时候在回答问题的时候必须仰赖这两个方程式。OK， 所以大家一定要熟记 Bernoulli 的 equation 跟 continuity 的这个 equation。好，那我们今天课就上到这里，然后耽误大家的一点时间，抱歉。那希望下一次考试大家在上传解答上可以没有什么太多的问题。那有同学寄信来问一些上传答案的这个状况，所以那我这边也都有进行回复。那希望同学在下一个礼拜一的考试可以再多加的注意。好，谢谢。我们今天课就上到这里。OK， 停止。